Real-world experiments. We deploy the algorithm on a custom-built, fully onboard autonomous AAV to conduct flight tests. In a wooded corridor, our AAV flies back and forth between two targets 17 meters apart, continuously evading surrounding trees, crossing pedestrians, and oncoming pedestrians. The bottom left shows the AAV's first-person depth observation and the spatio-temporal trajectory generated by real-time inference, while the bottom right displays RViz for auxiliary trajectory visualization. The second flight scenario is a forest, where the AAV successfully evades static trees and dynamic pedestrians, even under poor lighting conditions. Indoor flight. In a cluttered indoor scenario, the AAV flies back and forth between two targets 9 meters apart, still maintaining a 100% success rate. In this scenario, the AAV needs to continuously evade two pedestrians and a wide cuboid in the middle. High-frequency replanning enables the AAV to adjust its evasion path in a timely manner. Simulation benchmarks. We benchmark the proposed method against 4 SOTA methods in the field of autonomous flight in identical mixed static and dynamic scenarios. Benchmark comparison experimental data. Ablation experiments. We also conduct a series of ablation studies to analyze the significance of each module designed in our method. The results indicate that every component is indispensable. Design of groups for ablation experiments and planning performance results. Generalization discussion. To validate the generalization capabilities, we conduct flight tests in static forest, cluttered indoor, and crowded corridor scenarios. The results demonstrate favorable generalization capabilities across diverse environments without requiring any scenario-specific training or parameter fine-tuning. It also demonstrates robust flight performance in a scenario with faster-moving obstacles. Scene generalization performance and the performance boundaries. Methodology. Euclidean sign distance fields, or ESDFs, have been widely adopted for safety gradient guidance in static autonomous flight. However, they face critical limitations. First is the high computational latency. Second is the observation-supervision mismatch. For dynamic obstacle avoidance, modular pipelines commonly leverage the detection and tracking of moving objects, or DATMO. However, they also face critical limitations. First is the high computational overhead. Second is overly conservative behaviors. To resolve the computational and logical bottlenecks of previous methods, this paper aims to develop a novel safety gradient guidance framework that features 4 outstanding characteristics. First, this framework is fully differentiable and efficient, supporting GPU accelerated parallel generation during training. Second, it enables a unified representation of static and dynamic obstacles. Third, it utilizes an unstructured scene representation. Finally, it guarantees strict causal alignment. By confining the privileged gradient guidance strictly within the camera's field of view, We fundamentally prevent causal confusion in self-supervised learning. We name this novel Safety Gradient Guidance Framework the Temporal Polar Gradient Field, or TPGF. Initially, unstructured privileged scene point clouds are projected into an ego-centric frame to construct a Cartesian occupancy representation. This is subsequently transformed into polar coordinates, yielding the ego-centric polar occupancy grid, characterized by an elegant rectangular topology. A multikernel separable Gaussian convolution is then applied to efficiently generate the polar gradient field, as displayed in this workflow. Specifically, once the network generates a spatial temporal trajectory over a fixed horizon, we sample NPGF frames within the FOV at regular intervals and stack them along the temporal dimension to construct the temporal polar gradient field, TPGF. Finally, supervision gradients are queried from the TPGF via bilinear interpolation based on the trajectory's space-time polar coordinate mapping. Equally importantly, our polar representation offers three key advantages. First is FOV isomorphic mapping. Second, it provides a rectangular topology for deep learning. Finally, it features an adaptive spatial resolution that perfectly matches receding horizon planning. Before employing TPGF to guide the second stage planning policy, we introduce an offline ESDF-guided learning phase. Using carefully designed loss functions, we train the optimal multikernel Gaussian convolution weights via gradient descent. Finally, the calibrated TPGF is deployed to guide the safety loss in planning policy learning. We evaluate the computational efficiency of our proposed TPGF against the ESDF. We conduct this comparison across varying batch sizes and trajectory sampling counts. As shown below, TPGF significantly outperforms the ESDF across all tested configurations.